Okay, I'm going to go ahead and get started. I see several of us here. Alexa, Amanda, Caleb, Conley, Suzanne, excuse me. Glad to have you all here. I'm going to mute all of you to make sure that your sound is all muted so we don't hear the dog barking or whatever. Anyway, we're at module number 2, okay, and module number 2, pardon me, module number 6. This is the 2nd of October. And you're going to take a look at a couple of things. We're going to review Foster and Gorman, and then if we get some time, we'll look at the Wednesday materials, and that's the screencast. We'll look at ice cold, and we'll talk about them here for just a moment. The Foster case, okay, and find the pages for it. Just a second. We did data development here. The Foster case is, let's see, that's going to be over on, that's the transportation case. That's on 276 to 278. And that's involving that company with the shortest route problem, okay? Well, that's Gorman. Let me find Foster here for just a second. Hang on a sec. Let's see. I think Foster is going to be 308 to 310. I'm sorry. Yeah, Foster is 308 to 310. So my apologies. Had it marked and didn't look at it. Page 308 to 310. And this is another one of these as we move into looking at some of these transportation problems that we're going to be working with. Now, again, as they start over there on page 308, and those that might join us a little bit late, don't worry, it's recorded, so you won't miss anything. But 308 starts with what we call a transportation problem. This is the Foster generators, and there at 309 they give you the solution for the problem in Excel. And so let's go ahead and for a moment, and we'll go take a look at the files. I'll find the Foster file. And we'll go from there. Okay, and here's the Foster key. Now, I'm going to publish it now so we can all see what it looks like, because I'd ask you to do some things if I'm not mistaken. And go ahead and download Foster and take a look at it. Now, when we get into some of these logistics-oriented problems, and you guys are listening to look at the recording later, you'll want to note we're dealing with a couple of issues. One is what we call just a straight transportation problem, and that's from one node to another. The other is what we call what's known as a transshipment problem, and that's one that's really just external to a company. And again, they give us some information about Foster. It's over on 308 to 310. And you look at it, as you take a look at it, they start to show you there at the bottom of 309 all of the different, the decision variables, okay, the objective function, and then the left hand and the right hand sides. Now, I'm going to go ahead and move this, all right, and let's see, I'm going to click on data. And they'll look at the solver, and you can see we've got the objective is to minimize the cost. That's cell C13, all right. And then we had, by changing the variables, okay, and we had those variable cells to change, and that's B17 to E19, and that's basically these cells that are all in here, B17 to E19. And that's the destination, okay, at the origin and the destination, okay? And when people use the term nodes, that's what they mean, the origin and the destination. And when they talk about the arc, they're really talking about the distance between the two, okay? And so I ask you to go ahead and compute the minimum cost given the following supply values, okay? And I added 8%. Cleveland, I added 8% to it, okay? And then Bedford, I added 9.4%, and then York, I added 4.9%. And to have us run the solver and take a look at what we've got there. I think, and that's really about all there is, really all that there was to do with that. And again, we get a cost minimization factor. Now, if you look at page 309 in the textbook, you're going to see something different. You're going to see the minimum cost there for Foster generators is $39,500. And you say, okay, what is it that changed here that made you able to, how were you able to get this down? Pardon me, why did this go up? Excuse me. And yikes. And the reason that it went up is simple. We're handling more material. And the more material we handle, the greater the cost. That's all that's going on there. So it's a pretty simple transportation problem. And we talked some last week about networks and network problems. Okay, and that was really a page. Well, starting with page. They give you some self-tests on finding network nodes, but really the heart of all this is over back in chapter 6, where they talk about how networks are constructed. And really what you really have is you have what we call a node, and that's an arrival or a destination, or it could be both if you have stuff running between each other, coming and going. And then you have the arc. And that's the distance or the time, okay, or maybe an expense associated with that. And so, like today, everybody's figuring out how do they get all of that stuff down to Puerto Rico, how do they get everything down to Houston and down to down to West Louisiana, and how do they get stuff down to the Florida Keys, etc. And there are people diligently working. Some pretty more sophisticated, far more sophisticated models than this, okay? But you could see and we have some constraints, and the constraints is they walk us through a B20 to E20, okay? And they've got to be equal to B22 to E22, and we'll take a look at that, okay? Now, our constraints are B20 to B20 to a B22, so let's find that. We'll find B20 to B22. Okay, here's B20 to B22. Okay, those are our constraints, B20 to E22, excuse me, and then B22 to E22. So they all have to equal out, all right? Now, you'll notice, again, as we're moving more supply, as the volume of supply goes up, which is what we increased, you notice that the minimum cost went up. And so when these folks doing these disaster recoveries say, we're overwhelmed, all right, they truly are, because first of all, they're probably trying to intake more than they normally would. So even if they're shipping, let's say their ports, for example, had been untouched, all right, they'd still be overwhelmed because the amount of stuff coming in. All right, people don't build ports and capital structures of that type of capital investment without anticipating what will be the normal inflow. And Puerto Rico is a place, okay, that's going to be handling a lot of particular types of materials, but not of the scale and the scope that they were lining up. So those costs are escalating. Now, you could also say how much time. And that's why the time is escalating there, and it's putting people into some frustration. So I had you change the supply and to take a look then at the cost minimization. Now, we did find a solution, okay? And we do assume right here on the simplex that we assume using this that the data are linear in nature, okay? We assume that they're linear in nature. And in other words, as supply and distance go up, costs go up. All right, and that's just the nature of the beast. Now, if I had reduced these supplies, okay, we might have seen them go back down. In fact, and I'm going to go over to page 3, and you want to go back over to page 308 again for just a second, okay? That's page 308 in the text, and you look at the top of 309, and notice, okay, the supply is 35 for Boston, Cleveland and Boston. The origin of Cleveland to Boston is 3,500 units. Okay. Okay. And here we increase them. And I'll just click on here the formula bar real quick. And so we've got the minimum costs worked out there. Okay, and we changed the supplies for Cleveland, Bedford, and York, and those are the origin points, and that's what we changed. Notice York, for example, okay, it's 2622. That's about 5% more than what it is in the book. All right, Bedford, we increased it, but we don't have anything from Bedford in the first place, so it ended up being a 0 anyway. Now, we'll put this in the Cleveland would be 8.6%, so that's going to equal 3,500. Okay. Okay, times 1.086, and we'll okay. Now, when I devised this key, I left the Cleveland there, and I didn't adjust it upwards. I just put a number in there. Actually, I put a number in lower. Okay, but if you follow the algorithm I asked you to do, okay, you'd put it in 806. Then you'd see the minimum cost climbs even more. Okay, so that's the Foster case. They ship generators, all right, and again, the key thing is the decision variables. Okay, and that's B17 through B19, and that's how much, what type of supply level will we have. Okay. And then we have the objective function, okay, and that's at cell C13, and we use a sum product in there. I'll click on here and I'll show you. Okay, now if you stop and think about this for just a moment, all right, again, as you increase supply or you increase distance or both, transportation costs go up. You say, well, any simpleton would understand that. Yes, but what this means, though, what this means is that for Foster, they're probably going to have to do some thinking about their pricing. They're going to have to do some thinking about their about the marginal costs that their marginal contribution, the contribution margin, excuse me, and may have to make some adjustments. So that was Foster, okay, and we find there is a minimum cost there, and you know, we could run a sensitivity report and all that business, okay. But what we found is that when we change the supply levels, the costs go up, and you can look at, if you look on page 309 down there in cell C17. Let's look at Cleveland to Chicago. Now, originally, Cleveland to Chicago was 1,500. That was the supply, the units of supply. Now we're going to handle, Cleveland's got 8.8, it's going to be 1,500 times 8.6%. So there you go. Okay, and that's why it changes. And then notice those totals all change, and those totals have to be equal to or less than, okay, those over on H. But in fact, the totals are greater, okay, so that constraint isn't operative. Although we tried, we found the minimum cost because we found the minimum costs, so we got to be equal to or lesser than. And here this is higher when we look at the total for Cleveland. When we look at the total for Bedford, okay, it meets the constraint. And when we look at the total for York, I'm right here on 19, it's the same. So we've got kind of a mixed bag when we look at one that's higher than the constraint, one that's less than the constraint, and one that's right on target. And this shows you this whole idea of optimization. Okay, that's the whole point of this. Now, that being said, well, I'm going to diminish this for just a second, okay? And we'll go back over here and we're going to take a look at some more on our modules. And we did start a little bit early today, so we're in pretty good shape. And we're over here on module 6, okay? And we also need to review the Gorman case. And talk about Gorman, okay? And Gorman is over on pages 276 to 278. That's the one that I was trying to work with you there for just a second. So let's go back up to the files, okay? And let's find Gorman. And the Gorman key, and I'll publish it. Okay? And then I'm going to download it. Okay? And I'll enable the editing. Now, you've already uploaded your work, which is what I ask you to do each time, is try the case, and then I like to show you, the correct answer so you can learn a little bit from it and not get all wigged out about being crazy. This is Gorman construction. It's over on page 276 to 278, and this is a shortest route or path between two nodes in a network, okay? So we've got a shortest route problem. If you look at the bottom of page 276, you're going to see each of those nodes, okay, starting at Gorman's office, all the way over there to point 6. You're going to see some distances between those nodes, okay? And that's just a straight node. Notice, for example, I'm going to start Gorman's office, and you have to have your textbook to really see this. I'm going to start at node 1, and it's a distance of 25 over to 2. Then the road distance from 2 to 6 is 39. If I go from 1 to 2 to 4, I'm looking at 30. If I go 1 to 2 to 3, I'm looking at 28. If I go directly from 1 to 3, I'm looking at 20. So you can see how we use things like PERT, the Program Evaluation Review Technique, which looks at these kinds of, and the CPM critical path method to determine what's the critical path, the one that takes the longest. Now, this gets amplified or gets a lot more complicated, excuse me, when we start to talk about transshipment problems. And this is what I alluded to earlier, okay? A transshipment problem is one of those, okay? When I've got stuff flowing back and forth in a network. Figure 612 on page 276 is a single focused network. It's an outbound network. It's sending stuff out. And there are many of those, okay? Now, Gorman, at the top, the shortest route problem, here now they're assuming that you've got flows in between them. And if you want to see the direction of the flow, that's the arrow, okay? And so here's what's going on. We've got the origin node, that's 1, feeding 2, 3, 4, and 5. And then 2 is feeding 3, 2 is feeding 3 and 4. And 4 is feeding 5, and 3 is feeding 5. And then they all, then nodes 2, 4, and 5 feed into node 6. Okay? So when I ask you to increase the arc distance there, Okay, and let me start from before I get there. If you look at the bottom of page 277, this is why when you do these cases, you really do need to have the text open. Okay, and in those passages where we cover the case, if you want to get some understanding, which I would assume that you want to do, because you're going to have these types of issues, or whether you know it or not, you'll be affected by them one way or the other. Now, if you look here at the bottom of page 277, you're going to see the flow in and the flow out for each node. And as I had alluded to just a minute ago, node 2 has x2 plus x2 4, which is 2 to 4, and x2 3, x2 4, and x2 6, which means 2 flows to 3, 4, and 6. It does not directly flow to 5. Then node 3 flows directly to 2 and flows directly to 5. Now, on the right, the left hand, now you say, oh, okay, you're about to tell me here's the left-hand side and the right-hand side. Exactly, because we've got the stuff that flows out and the stuff that flows in. The volume, well, the directions, the arc sizes. And so I'd ask you to compute the total distance, okay, given an 11.1% increase in arc 1 and a 2.8% increase in arc 5. Okay, and so we do that, and on arc number 1, okay, I have a distance of 2775. Okay, and if you go over and you take a look in the textbook, what you're going to see, okay, is the bottom of page 276. You'll see that originally, okay, the distance between the arc or the distance between node 1 and 2 was 25. So I added 11.1%. And I also did a decrease in arc 5. Now, as I've said before, we use this tool, okay, to understand how changes in variables, okay, can to let us see a range or a continuum of outcomes, not just to believe that there's just one really great outcome, because there often is not. You often have to pick or choose, or at the very least, okay, run through some of these scenarios, okay, use Solver, or a transportation company would use its nodes. It would use some proprietary software probably, and they'd run many iterations to see what looks like the best one. Now, incredibly, people like FedEx and UPS have used cloud computing supercomputers to do routing on a daily basis. Can you imagine the complexity of that? And they probably have an entire staff of people that do nothing but input figures into the software, input figures and get figures from each of their stores and their outlets, and then people who knows how many people they've got behind the scenes working all of that. In addition, not only do they just have people are putting numbers and running them through a statistical grinder, you've got to have people there who are watching the weather, who are watching traffic. So, you know, when you ask me what companies do you admire, okay, I'm going to say that I admire that I think are incredible companies. I'd say Walmart is one. I'd say Amazon is another. I'd say UPS is another, and I'd also have to say FedEx, because of the incredible amount of work. The only people that have node or network problems as complex are people who run the phone companies and run internet service providers and cable providers, okay? And for them, it's just unbelievable. So when you hear the power is down in so-and-so town, and then when you hear people say it's going to be months, maybe years before Puerto Rico fully recovers, they're not fooling, because if you see pictures of the place, everything's gone. All the infrastructure is gone. it's destroyed, it's damaged, it has to be rebuilt. And that means they'll have to rebuild their whole entire communications infrastructure that's been in development, well, ever since they put the first phone systems in Puerto Rico. I have no idea when that would be, okay? But you can go back and find out. So again, you start to see how complex these are. Now, this is the shortest network, okay? And Gorman, okay, is, they talk about there on page 276. There in that second paragraph. Yeah, the Gorman shortest route problem can be viewed as a transshipment problem with one origin node. Node 1, that's the Gorman's office. That's node 1. Imagine how complex this gets if you have multiple points of origin, okay? Then it really becomes exponentially far more difficult. And that's why I would say, people out in logistics are always looking for very intelligent, highly motivated people and who can see this and understand it, okay? And you go work for one of these companies, they're going to do okay for the simple reason the more stuff people buy online, the more stuff these people carry and handle, because you ultimately have to get it. And I'd say right now, the enormous job that's going to be going on down in Texas, okay, in Western Louisiana, in Florida, and in Puerto Rico, and the Virgin Islands, it's all there through the Caribbean, okay, is going to be a logistics case study for the next 20 years. That's how devastating that all was. And I put it in that context. And then let's not forget, you have the issue of Mexico City. Now, I think I had put a link over there, or sent all of you a link to an incredible graphic created over by the New York Times that shows that Mexico City sits on some very unstable ground, okay? And because it does, when the earthquake occurred, all right, the level of shaking was very severe. Now, the further you get away, the less severe, and the more dense the ground becomes, the less severe. That's why in Oklahoma, when we've had these earthquakes of 5, I think we had a 6 magnitude. And I remember it. I was at home at the time. I was living in Moore. I was on the east side of I-35. They had a I think a 5 or close to a 6 up in north. I can't remember the specific place, but I heard a huge boom, okay, and then my house shook. I thought it was an explosion, and then I was in it. We had a spate of them there, okay, and we were feeling it. And one of them, literally, I stood and I watched as my house undulated. The floor just kind of looked like it had a wave, and it scared my wife to death. And the reason is because Oklahoma has a lot of sandstone. We don't have a really dense type of floor. So these kinds of problems these techniques are very universal. And this is one of the things I can't emphasize to you enough, that understanding this you may not get the perfect solution, but if you utilize optimization and you understand these models like a transshipment network problem, you're going to understand quite well the kinds of issues that you're going to run into when you deal with this. And again, here we increase the arc distance, arc 1 distance, and we increased and we did a decrease in arc 5. You said, well, okay, were you just playing with numbers, or what are you trying to show me there? Well, it's very simple. Transportation routes change all the time, okay? Any type of transportation route, whether it's a highway, okay, something that carries people in cars, whether it's a network that carries electricity, whether it's a network that carries internet feed, whether it's a network underneath us of gas lines, okay, of natural gas, oil pipelines, water, anything that carries stuff is a dynamic system. Okay, now I don't want to get too far afield with this because this kind of takes you out of the realm of management science and into logistics. But the study of logistics is, how do I logically approach dynamic systems? Okay, how do I approach that? How do I handle that? All right, and the problem that I gave you here is a baby problem, but very typical, because, for example, let's say arc 1, all right, the distance increased because there's construction. All right, you don't have to drive too far outside of you don't have to go too far west. In fact, if you go on 77 and get on the Highway 40 head back to Oklahoma City, you have to deal with construction. So that the time, okay, is increased. And then if you've gone on vacation in the summertime, you might as well plan for getting caught in a lot of construction, because that's when people get out and repair their highways. Then we see a decrease. And let me give you a really good example. In northwest Oklahoma City, okay, traffic was a nightmare until they got the Kilpatrick Turnpike. The Kilpatrick Turnpike basically siphons off tons and tons and tons of traffic, although there are still lots of people like me too cheap to buy a pike pass, and so I get to drive on the regular streets when I could get on that turnpike and go right out to 35 quite easily. It feeds into 77. I mean, it's nice. But again, I'm one of those people, I don't want to pay the pike pass. If you take the turnpike, the Turner Turnpike, which was built within my lifetime from Oklahoma City to Tulsa, okay, you can leave Oklahoma City and be in Tulsa in an hour and a half, maybe 2 hours. At one time, you took Highway 66, okay, or 44, all the way up. There was no I-40. You didn't have those. So you could see the kinds of things. There may be a big, gigantic wreck. I remember, and I've been driving back between Oklahoma City and Shawnee for over 10 years. And I remember one day I was headed home, and there was a horrific accident up over by Peebly Road. And I mean a bad one, but a semi-trailer, several cars, and we all sat there for about 2 hours before we could move out. It was an hour and a half, probably 2 hours, and the traffic was probably lined up 30 miles because people would just pull up and they'd stop and they'd sit, and then you'd get what happened was eventually the Oklahoma Highway Patrol would drive down the side of the road, and they had a speaker that said, "There's been a bad accident, blah, blah, blah. If you can get off and if you can reroute yourself, you'd be smart to do that." So those are the kinds of things that change the arc distances. Okay, and again, listen, this I can understand, or this may not be something that just gets you totally revved up. By the same token, let me say this. This is the kind of thing, the type of skill set or the type of tools that can make people's lives better. Imagine if you're talking about not shipping stuff, but getting emergency technicians to a home, getting them back to a hospital, shipping highly sensitive material, getting human organs from one place to the other. People somebody has to have open heart. Maybe they have to have a new heart or new kidneys. You got to move that stuff and move it fast. Okay? It's highly perishable, as you would imagine. So those are the kinds of things, and we're going to see enormous amount of work done. And like I said before, that whole area that has had that horrific disaster is going to be a case study in logistics for the longest time. Now, since there are a lot of talking heads out there, and I've worked in the field, I've got a master's in operations, I'm going to throw out my 2 cents. The first thing I would have done was take every C-47 I can get my hands on and start dropping food, water, and supplies to people who were remote. Then begin to work on ports and facilities. But someone somewhere decided, okay, that they would try to get the big facilities open and then open the pipeline. But this is an opinion of mine and only my opinion. They are going to run into what we call the last mile problem, and that is once I get off the main highway, I get into dirt roads, primitive driving conditions, etc. And that's when things get tough. So I've watched and I've just wondered, why has it not dawned on somebody that we ought to just do a humongous, tremendous airlift? But that's just my own opinion, okay? And I would say this: I'm certain that the people up in all of those offices are working as hard and fast as they can to get as much stuff to as many people as fast as they can. But they've got some real problems because of what they can receive. So this transshipment problem is a really good one, and to help us understand the kinds of issues that we run into. And just imagine how complex it would be if I had several origin nodes, okay? It would be just incredible. So that's the Gorman, okay, and Gorman construction case, all right? And let's go back up to the modules for a sec. And I do appreciate you being here. And, we got started a little bit early today, about 10 minutes early. So, we're a few minutes from being over and done with this. But this is, again, we're over here on Module 6, okay? And I have a couple of files here. And I'm going to talk about Wednesday the 4th. I want to spend some time on the ice cold case, RMC, and Martin Beck. Okay, and I'm going to ask you to upload them. Now I have keys, okay, that we can look at. I have keys that I've got unpublished, so you're seeing those, okay. Martin Beck explained. Now notice also you have some quizzes coming up, okay, and then I've got some additional resources for you here. And I want to walk you through them just quickly, okay? Because they're apropos. It's always good to kind of take a look at them. And this is again looking at project management and capital replacements, and looking at the 3 kinds that we run into. Are they mutually exclusive? Is it a straight replacement? Or are these independent projects? And you'll want to take a look at that resource, okay? Because it will be a refresher for you from your finance course when you did some capital budgeting problems. But I think it's important for you to see that, okay? And when you take it and you put it within the context of what's to be some of these cases we have coming up, it does help you understand. Now, not to be too pedantic, but I also want to really encourage you. Now, I don't give you tests over this stuff, quizzes and so forth. And I've had students say to me, why don't you give us a quiz? Well, I guess I could, but the bottom line is I'm trusting that you are committed enough to your professional growth, that you're mature enough at this stage of the game to say, I need to learn some more about that, or I need to be thinking about that, or here's another resource. And this is talking about order and setup costs. Now, those of you who've had business problem analysis, remember that we did an inventory problem, okay, where we had setup costs. We did an economic order quantity problem, EOQ. We had setup costs, order costs, and total costs, okay? And the 2 variables there, ordering costs are traditionally are traditionally thought of as fixed costs or a proxy for fixed costs. Setup costs have traditionally been considered a proxy for variable costs, i.e. costs that change with the volume of business activity, okay? And so you could take a look at this, and this walks you through the question of how much does it cost your company to place an order, okay? And that's, you know, that's something you better have a handle on. Even if you're a distributor, if you retail stuff, you have to have a handle on that. So I provide that resource, which provides that overview. And again, you have to remember, when you work with a model like this, order and setup costs, so you're going to assume, okay, the order and setup cost is your total cost, okay? And he talks about the carrying costs, okay? That's the cost of having the stuff on site and setup. That is manufacturing companies. If you're Dillard's, you have setup costs. You say, what are you talking about? If you're Dillard's, you got somebody that goes around and puts clothes on mannequins. You got somebody that goes around and makes sure all the socks are lined up nicely. Somebody that goes around and makes sure all the stuff out on the counter is arranged very nicely, that you have the prices right. Those are setup costs. You absorb those. Okay, so the total cost of inventory has to be figured on that basis, and so you have to have a handle on that. Now, the other resource that I want to encourage you to take a look at, okay, here is a classic model in the Northwest Corner method. Now, let me say this: operations research, management science, logistics are terms that are often used interchangeably. The truth is they mean some different things, okay? But the bottom line is all of them are an attempt to take a model, to construct a model and apply it to the real world to either minimize, maximize, or hit a target value. Most of the techniques we have, like linear programming, which the Northwest Corner method is one of those, were born during the logistical issues created during the Second World War. If you would like to see something that's an incredible marvel, go back and read about the D-Day landing, okay? It's history now. I understand that. It's 70, 80 years ago. Okay, I get that. But think about it for a moment. All right, the Allies landed hundreds of thousands of people, men, and pieces of equipment, the greatest armada ever assembled, and put them on the shores of France. Now, the only thing that was even close to anything like that at the time was the famous Dunkirk withdrawal. That was the British forces early in the war were trapped in the sea at a place called Dunkirk, and there were the Germans and the sea. And so the people in England, who are a seafaring people, got every seaworthy vessel they could get and went out and rescued those people and they saved England. And that probably was one of the most pivotal things that kept the Germans from winning the Second World War or being in a position to negotiate, for the simple reason that they didn't have air cover. So that's a resource I'd like you to take a look at. And again, all of you are out there. I'm going to make sure Alexander, Amanda, Conley, Josh, Suzanne, Caleb. Again, I really appreciate you being here, and I know I'm going to have others who will look in later on. Now, this is one of those resources that I'd like you to take a look at again. And see, I give you, when you get one of these surveys and they say, did the instructor challenge me intellectually? This is how I challenge you intellectually, to see if you are willing, okay, to go the second mile in your career and learn and read some things that would refresh your learning or extend your learning. So these are some ways that I can do this. It shows you some jobs in logistics, okay? And these are logistics and supply chain jobs, and there's some fantastic companies. There's some great opportunities for you. And I hope some of you will be smart enough to take those opportunities and run with them. So there's a search engine for you, okay, to take a look at. This is a resource on careers in logistics and supply chain management. And then here are some Bureau of Labor Statistics data on job prospects in logistics that are pretty fantastic. Well, it's 11:43. We've gone over 50 minutes, okay? We pretty much achieved our objectives. We looked at, we wanted to look at Foster and Gorman, okay? We didn't have time permit to take a look at ice cold. We're going to look at ice cold, RMC, and Martin Beck, okay, on Wednesday on that screencast. And I do appreciate the 7 of you here. I know we'll have a bunch more folks who will be taking a look at this video cast. So thanks a lot, and have a good one, and we'll wrap her up.